lot of situations where that's true, but for every normal force pointing up, there's gonna be one pointing down. Forces always come in pairs, and each force in that pair points in an opposite direction. Here's a situation right here. There's a normal force acting on me from the wall, pointing that way. At the same time, I'm pushing that way on it. So there's a normal force on the wall going that way. Normal force prevents one object from going through another, whichever the orientation is.
Oh, okay, that makes more sense.
We usually think of, ground as sort of a constant, but in physics, you really can't do that. You should be able to look at any problem from a different point of view and still get the same answer. So we generally think of it as, I got a world here. Please work. I got a world here and I'm standing on it. It is equally valid to think of, I'm here and I have a world balanced on my feet. There's no reason to think that this is an invalid way of looking at it. It's not necessarily mathematically the simplest way, but it's still a valid way of looking at it. So I'm pushing down on the Earth is pushing, well, the way I've drawn it here, down on me or up on me from this point of view. I don't know whether that look is, you answered my question 5 minutes ago, you should have just stopped, or whether I just made it worse.
No, it's not getting worse. I just I had never seen you explain that. And that was a question on the master test. So seeing it is like making it
Okay,
click.
yes.
So no matter how high you stack up objects, like if I have a stack of 5 objects, from each object, the weight of this object and the weight of like my top object and my middle object, both of those weights are gonna be up forces on the ground.
Yes.
Not on the object thereupon.
Correct.
Got it.
Which is why, to go back to the example again, if, I make it sound like my brother jumped on me a great deal. It happened more than once, but probably it wasn't a regular occurrence. But if my brother's on top of me, because he was bigger, and he's bouncing on me, I'm definitely feeling more than his weight. So that's another way of thinking, oh, it's not the weight that's acting on me, it's actually the normal force.
Okay.
Of course, he could counter from a physics point of view. I was pushing on him with just as much force as he was pushing on me. All right, so back to the initial question about why does pulling up mess it up? By the way, what did you use? What did you have on there? Was it
I used a candle.
a candle?
Yeah.
Just trying to get some sense of size of what you're working with. I assume upright candle or on its side? Upright, okay. Yeah, it's really hard to do it without that thing falling over. So, if I pull up, so now I've introduced another force in this direction. Then, wait a second, let me come up with a coherent answer.
In the video, you talked about it being friction and another force that we haven't learned about yet.
Yeah, I was gonna bring friction into it. Suddenly I got something backwards in my head, so, one moment. Alright. So if I'm pulling up on it, so right now I've got a normal force just because it's sitting on the tablecloth. When I pull up, I'm now accelerating it upwards, which means the upward force exceeds the downward force. So the force between the tablecloth and the box here will increase because I'm now pulling up. Friction, as we go into more detail later, friction is directly proportional to the normal force. This is the symbol for directly proportional to. In other words, if I double the normal force, I double the friction. Triple the normal force, I triple the friction. I cut the normal force in half. So if I increase the normal force, I'm increasing the friction between the tablecloth and the book. Well, since ultimately I'm trying to get the tablecloth out from underneath it, friction acts opposite of what I wanted, of the desired relative motion. And so on the box here, I have friction acting back this way. The tablecloth's going that way, wrong way. Friction's going this way on the box, and I've increased the friction, so I've increased this drag force on the bottom of the object.
Can you do it again?
All right. Tablecloth. As I'm pulling on this, as I pull up, I increase the normal force between this and the book. As the normal force increases, the friction increases. So now I have a greater force acting on this thing sideways. So it's more apt to get pulled in that direction. Whereas if I'm pulling down, I'm not applying that extra force. Any additional force I apply if I'm pushing down is going to affect the table and not the box. And so as I'm pulling this way, the greater the friction acting on it, the more apt this is to get dragged along with it.
Okay, so if you pull up, then you'll increase the friction this way. So,
Or actually, the friction acting on this is in the direction of the pull.
okay, so
Because, and let's talk a little bit about that. Ask your question, and then I want to get back to why the friction is in the direction of my pull,
so if you have a box and you have a tablecloth
right?
and you pull up, then the friction you said is directly proportional to the normal force.
Right?
So that will move the item together with the tablecloth?
More apt to.
Oh. I think that happens.
All right. So we talk about, I've mentioned in videos and song and story that friction opposes the desired relative motion. So if we think about this, I've got this mass sitting on the book right here. If I move the book this way, well, if the book were frictionless up here, what would this mass do?
Slide off. It would slide off
Which way?
the opposite way.
Relative to the book. Relative to the ground, it would just sit right there and this thing would go like that. But it's touching the book. So the desired motion relative to the book, that's why I say desired relative motion. It's relative to what it's touching. So relative to the book, this thing wants to slide backwards. Friction opposes that in the opposite direction. So the friction on this is in the direction of movement. Or the direction I'm sliding the book. We will touch on that in a little bit after the quiz.
Okay, so if you go downwards, does that mean you're decreasing the friction?
Actually, no. In this particular scenario, when you pull downwards, you're applying the extra normal force to the table. The ground has to withstand more now than it did before. But we're assuming the table's not sliding with you.
Where would you draw that?
So if the tablecloth gets pulled in that direction, so there's some force this way. It's an example of other. Then we would introduce, there's a friction force in that direction acting on the book, and then that way acting on the tablecloth, because forces come in pairs. And now there's friction between this and the table, so there's friction acting, let's see. So relative to the table, the cloth is sliding to the right, and therefore friction acts to the left on the tablecloth, and then that way, like this. Now, if the tablecloth were really stuck to the table, as you pull it, the table would come with it. So friction opposes that, so there's got to be a friction acting back this way, and then that way on the rim. So that's would be friction, assuming that we had this applied force acting on it. If you pull up, then it depends on how much you're jerking up on it. This force right here would just change direction. Possibly that, depends upon, now we start getting into situations of, you know, is the tablecloth now like that? But friction is gonna be parallel to the surface, whatever it happens, whichever way it happens to be. All right, other questions about this?
I was wondering if you could go over 32.
Ah. Okay. So they have 10 newtons and 5 newtons. Something better than this. Seven newtons and 3 newtons. 12 newtons and 4 newtons. And 3 newtons. Again, this is a situation of direction matters. These forces are fighting against each other. It's reducing the overall net force, that which is going to get it to change whatever it's doing. So in this case, that's the dominant force right there. How much more dominant is it? Well, it's 5 newtons more than what we had over here. So the net force on this is 5 newtons that way. On this one, net force, in unison would be really cool.
For,
Sounded like a single voice and a couple people repeating themselves. This one. And the last one.
0.
0?
I heard 0. And so just on a quick surface of it, you're adding them like that and rank the net forces from least to most. Now, please be careful on this one. Almost every ranking problem he does is usually from greatest to least. This is a situation where he's actually flipped it. So this would be the smallest magnitude of a net force, then B, A, and C. From a slightly different point of view, we're adding vectors. I have 2 vectors. I have one that's magnitude of 10, so I just draw that one down. And then I add to it another vector, which is in the opposite direction, 5 newtons. So now if I'm doing it graphically, scale matters. So the second one is basically half the length of the first one. And I end up with a resultant, well, basically from where I started to where I ended. So that's my resultant right there, which is, well, 10 minus 5, 5. From a slightly different point of view, why don't I make to the right positive? And just add them up. So it's positive 5 plus negative 10, which is negative 5. The negative here is just telling me it's in the negative direction, which is opposite the positive direction. That'd be 3 plus negative 7, negative 4.
So the positive direction always to the right?
Okay.
Okay.
It's
Do I-
positive this way because I said so.
So is it always based off what I say?
Yep.
Okay. Should we write that and like, when we do like work?
Yes, please.
Okay.
In a slightly different way. Let's make to the right I hat. So it's now 5 I hat plus negative 10 I hat, which is negative 5 I hat. 4 different ways of looking at the exact same thing. The answer definitely is not 15 newtons for the first one. Because direction matters. Emily, did that answer your question?
Yeah.
Okay. Ariana?
So when a net force is asked for, you should include direction, or you don't have to?
All right, so this comes down to, I think, some poor wording on his part, because he says rank the net forces on the blocks from least to most in the 4 situations. Since force is a vector, if I make to the right positive, now I'm ranking, so if I go with that, I have -5 newtons, -4 newtons, -8 newtons, and 0 newtons. Now asking to rank the forces, is a -8 Newton force bigger than or smaller than a -4 Newton force? So math class will tell you, well, -8 is smaller than -4, but now we're saying, no, wait a second, -8 is bigger than -4. Better wording for that question would be rank the magnitudes of the forces, in which case the minus signs all go away because we're not worried about direction in the end.
So in this case, we're looking at absolute value.
Yeah, that's the intent.
So when it asks for the magnitude of the total force, direction doesn't matter. When asked for the total force or the net force, assume direction matters unless the question implies otherwise.
I'm not sure I heard it completely the way you said it. Let me sort of pare it back and see if I got it right. If it's asking for magnitude, you do care about direction when you're adding them together. You don't care about direction at the very end.
Yes.
Okay. Yep. Then yes.
Okay, that was part of it though. And then the other part was if it asks for the, like when it mentions magnitude, direction doesn't matter in the final answer, but if it just says total force or net force, then assume direction matters unless the question implies otherwise?
Yes.
Okay.
Yes. That's the kind of thing on a quiz, I would make it clearer so that there's not this, one person that says -8 newtons is less than -4 newtons, and another person says it's greater than. Because now we're left with two different solutions which potentially are right. Noella?
So when it comes to like certain things, so like magnitude is the resultant,
Say it again?
so is magnitude the resultant?
Magnitude is the size of the resultant.
Okay,
Resultant technically is still a vector, so it has a direction.
okay,
Magnitude would be just absolute value.
okay. So like in the recent lab we did, when it was like magnitude of the weight, and we did like the formula, like weight equals mass times acceleration due to gravity, is that like what we always do kind of thing?
Yeah, usually when someone asks for weight, they are asking for the magnitude of weight.
Okay,
However, I try to be clear in the lab so there's not this question of, does he mean the vector or does he want the scalar here?
okay.
Which sometimes leads to way too many words.
Yeah.
It's my unfortunate solution to confusion is to add more words. But I like questions on quizzes and tests to have a single answer, but sometimes that messes up and there's multiple interpretations. Other questions on chapter 2? All right. Stop this, we'll do the quiz, then we'll move on.